My name is Natalia Verde, and I'm currently a PhD student at the Photogrammetry and Remote Sensing Laboratory of the Aristotle University in Thessaloniki. I was involved in the MaiL project during November and December 2019 in Task 2.3, Methodology Development of Mountainous and Semi-Mountainous Marginal Lands Detection. My work included the selection of indicators, criteria, and thresholds that were used for mapping marginal lands, as well as the development of a first outline of the methodology which was later implemented. In this video, I will present you the overall approach that was used for identifying and classifying marginal lands in the MaiL project, as well as which datasets were used and how to create a database using open source tools and software.
In the first slides, I will describe the overall approach and tools used for the identification and classification of marginal lands in the MaiL project. The scope of the MaiL project was the development of a common methodology for detecting marginal lands that will be applied in large areas across Europe. However, an important parameter affecting the implementation of this common methodology was the physical characteristics of each area. While the implementation of a specific set of indicators and thresholds would return adequate results when applied to a specific area, for example in South Europe, it would return unacceptable results when applied to another area, for example in Central Europe. Thus, within the MaiL project, the proposed methodology was divided into two main phases: the hard thresholds and constraints phase and the soft constraints phase. The first phase was applied uniformly across all European countries, while the second phase included the development of specific sets of additional indicators that were applied regionally according to the physical characteristics of each selected site. In the first step, the so-called hard thresholds and constraints were implemented by following a top-down, stepwise approach. Starting with the whole European area, areas that did not meet the requirements of the definition of marginal lands were incrementally removed. Such areas included permanent water and snow areas, agricultural lands, peat bogs, marshes and more, forest areas, protected areas, impervious surfaces and recently changed areas. This procedure was applied uniformly across Europe since the same constraints apply. In the second phase, additional indicators were implemented based on the thresholds found in literature. These soft constraints were factors with variable thresholds and were grouped by constraint type into four categories: terrain, soil, sustainability, and productivity indicators. These include biophysical factors such as slope, elevation, soil quality or fertility, and erodibility, which are inherent properties of the land or soil. The indicators of the second phase that constitute the soft constraints were firstly ranked according to their importance, which was the times a constraint was found in literature. After that, weights were assigned to each constraint based on a pairwise comparison matrix of ranks for three classes depicting marginality: 1. Marginal lands with high plantation suitability, 2. Marginal lands with low plantation suitability, and 3. Potentially unsuitable marginal lands. Thus, the classification of marginal lands for the soft constraints was performed by applying the calculated weights in a weighted overlay for each layer. The basic tool used for identifying and classifying marginal lands in the MaiL project was QGIS. QGIS is a free and open source geographic information system software that also supports Python scripting. You can download the software from this link, as we will be using it throughout the tutorial. In the following slides, we will see which were the datasets used in the MaiL project and how they were selected. The datasets collected in the MaiL Task 2.2 were filtered based on the marginality indicators and thresholds found in the literature review. The final datasets chosen were the ones which were closest conceptually to the marginality indicators and at the same time had the same units as the indicators from literature in order to be able to apply the same thresholds in the analysis conducted in the next steps. After the filtering, we ended up with 29 datasets that were finally used in the MaiL project. Some datasets were used for applying the hard marginality thresholds and others for the soft thresholds. You can download each dataset from the links provided in this slide. When downloading, choose the highest spatial resolution and the most updated version for each product. In the next slides, we will see how to create a geospatial database and load data in it using open source tools. The tools that we will be using are the latest version of QGIS that you downloaded previously, PostgreSQL, which is a tool for generic database creation, and PostGIS, which is a tool that connects PostgreSQL with QGIS and allows PostgreSQL to process and store geospatial data. First of all, find the latest version of PostGIS from the link provided and download it. Find which PostgreSQL version it uses by checking the executable file name. For example, here the PostGIS 3.1.4 version uses PostgreSQL 9.6. Next, go to the PostgreSQL site and download the respective PostgreSQL version. Here it was 9.6. Install PostgreSQL using the default settings and without Stack Builder. Afterwards, install also the PostGIS version you downloaded before. Again, use only default settings. When the installation finishes, add the PostgreSQL bin directory to your Windows path in order to have access to other tools available in Postgres. Now, in order to create an empty database, open the PostgreSQL application called pgadmin, and by right-clicking on Servers, create a new database. For creating the extensions that will allow Postgres and PostGIS to connect, go to Tools, Query Tool in the main menu and type Create Extension PostGIS and then hit the play button. Do the same by typing Create Extension PostGIS Raster. To add vector layers to the database, open the PostGIS application and click on View Connection Details to type the connection details of your newly created database. Click on Add File and select the vector dataset you want to add. Then click on Import. To add raster files to the database, use the raster to PGSQL tool through the command prompt by typing the command shown in the image. In more detail, raster to PGSQL is the PostgreSQL tool for raster import. S3035 is the spatial reference EPSG code, here it's the European reference system. TAuto is for automatically specifying the tile size in which the raster will be splitted to. I, M, C, and F are some other settings needed, and then is the path to the raster file we want to import, and the schema in which to import and the name of the file. Following the PSQL command are settings related to the PostgreSQL and the database connection. Finally, to connect the database created to QGIS, go to the QGIS browser panel, right-click on PostGIS and click on New Connection. Fill in the settings and click OK. You should see the database layers under the connection you just created. Now you can drag and drop the layers of the database you want to work with in the QGIS layer panel to load the layers. We will now see a demonstration on how to create the database and add the downloaded datasets in the database and then in QGIS as we described previously. Thank you for your attention.